Good morning, everyone. Let's be honest. I know that maybe your brain is already waiting in line for your lunch buffet, but we promise you that we will be like a good alt-text, quick, helpful, and easy to digest. Today we're going to talk about alt-text application developed to create accessible ebooks for people with visual impairment with the use of artificial intelligence. These are the main topics of our journey today, and let's dive into. People with visual impairment use a screen reader to access digital content. Screen reader read the text out loud. And for example, if there is an image without alternative text, it will just say image, which doesn't mean anything at all. And since in Italia we use images to convey meaning and information, we decided to add alternative text to our image. In this way, students with visual impairment can interact and solve our exercise with images independently, like their peers. But what does alt-text do? Alternative text conveys the purpose of the image, and it has a limit of 150 characters. If we are dealing with complex visual content, we can also add a long description with more details. There are several benefits of alternative text. First of all, it can be seen by screen reader. It improves search engine optimization, and if you have a poor connection, it appears if the image fails to load. And what about European Accessibility Act? It is a law introduced by European Union, which imposes that all digital products and services must be accessible by June 2025. In our case, we are talking about accessible ebooks. It requires WCAG compliance based on PUB principles, meaning that a digital content has to be perceivable, operable, understandable, and robust. The first principle, perceivable, says that non-text content needs alternative text. For this reason, we are here today. And why we are using artificial intelligence? Because we are dealing with millions of images. For example, if you think that we produce 160 ebooks per year, which contains around 800 images, it means that we are dealing with 130,000 of images. And what about the catalog? Just guess a number. Since we wanted consistency and quality across the entire catalog, we developed an application which uses artificial intelligence to generate alternative text reviewed by our editorial teams, and for this reason, we can talk about a human-in-the-loop approach.
Yeah. And so let's describe our first monolithic solution. The task is given an ebook generate the alt text for all its images, and then insert those alt text back inside the ebook. We accomplished it with a Python job that uses generative AI to produce the alt text, and then we started designing some additional features like being able to explore and edit the alt text that we produced, and also repeat a single task, and so on. We needed to introduce a database to perform these tasks, and also an API to carry out the CRUD operations. We also needed to trigger the task, and we describe later on how we did that. For our efficiency constraints, the monolithic solution wouldn't suffice, so we moved on to a modular solution that will be described also later on in the presentation. In order to handle the ebooks, we decided to use the library ebooklib, which simplified the process of extracting all the images inside that ebook, and also the textual context next to the image, which is very important for our use case. And furthermore, ebooklib also allowed us to edit the ebook with the alt text that we produce. But there's also a limitation in that library. First of all, we cannot load the ebooks from a stream, for example, from a S3 bucket stream. So we had to load them only from disk, so downloading every time the ebook and then loading it. Then we had some issues with writing back the modified ebook. Some files were not maintained from the original book to the modified ebook with the alt texts. So we used a beautiful soup-based workaround that uses EPUB to extract the HTML version of the book and all its images. Then we modify that HTML with a beautiful soup, and then zip everything back manually, retaining all files, metadata, and all the important information that we needed. And so if you're here, you probably know Fast API, and it is an ASGI compliant web framework that is very suitable for fast prototyping, but also for production applications. And it is based mainly on two components, Uvicorn and Starlet. The first one provides the web server and all the functionality connected to it, and the second one provides only the routing, middleware, and the background tasks. In our case, having heavy background processes, we get that a nice feature essentially for free. It provides also a very native documentation tool through Swagger UI, and it can easily be integrated with SQL Alchemy, which we already used. And to model the data, in fact, we use the SQL Alchemy ORM, which, because of the two main features, the Pydantic integration that can derive the schemas directly from our ORM models for API validation. And using the same model for ORM and API responses is a very, very nice plus. We did not add any Alembic migration yet, but it is because we need only basic CRUD operation in our application. And we weren't sold on staying into the ORM until we experimented a bit more with other solutions. In general, pairing an ORM with a migration tool is a best practice, and it's in our roadmap. There is also a lively discussion about this topic in room Tagliatelle, if you're interested. When I say a monolith, I literally mean one Docker container that exposes our REST API and that is ready for our CRUD operation on the database. And then we download the ebook from an S3 bucket, as I said, for the issues of EPUB. And we stack then the images and the stored in context, call out to OpenAI to produce the alt text that we need, and then we reinsert everything back into the ebook. Everything lives into that one container. Web server, background workers, AI integration, file input and output, and the database access. This will be an internal solution, an internal application, so we expect around 10 users. But in any case, we had to deploy this application into an AWS AC2 instance to handle all the heavy background tasks that we need to run. As a result, the service is idle most of the time, and we would like to scale ingestion and AI generation independently from the rest of our application. Hence, we move to a more modular solution.
Okay, so basically, we have two main components, the API and the tasks. And the API should provide the authentication, the middleware, the CRUD operations onto the database, and also trigger when needed the task. While the task provide the ebook ingestion, the alt text generation, and the ebook publication. The two components share the code base, and right now they also share the same environment. It means, for example, once we load the ebook into memory, and we do that in the API, it's available also in the task. So we needed to make the task more and more independent from the API environment, and we ended up just needing the ebook ID onto which the task need to be performed. Once the two components have been separated, we were able to create two different images, containers. They still share the code base. We just needed a new entry point for the task. And then we could also customize the dependencies and the starting images because we wanted the API to be faster and lightweight. And also, we can now deploy them differently. since they're separated. So let's dive a little bit into the Docker files. Maybe there are something which can interest you. We mixed two optimizations for the Docker files. First, we used UV as a package manager instead of the most known PIP or Poetry. It's just way faster. And secondly, we adopted a multi-stage build approach in order to reduce the image sizes. The multi-stage implementation looks like this. You create a build image first, in which you install all of the dependencies you need, and you need to install them in a virtual environment. Let's call it .local. Then you create another image, a deploy image, in which you only copy the .local environment folder. In this way, you bring all of the dependencies in the other image without carrying in also the pip cache files or any other unused file. As for the UV part, it's quite easy. You just install it with pip. Then you create a virtual environment using UV. And then you use UV to install the dependencies as you would with pip or Poetry. So we were able to move from this build to this one. And as you can see, it's quite an improvement. In our case, what mattered most was the image size, but also the build time. It's an improvement worth mentioning. And obviously, we did the same for the API image, which was the actual target of this optimization. So now that we have two images, we can deploy them. And let's start with the task. We choose to deploy them AWS Fargate. We use usually AWS. And in order to do so, we first needed to implement a new class, a task manager. This is because using a background task in FastAPI is quite easy if you ever used it. And you just define the function and then run it in background. Startlet and FastAPI provide ways to manage the load, so limit background tasks and also automatically queue them. And furthermore, since the task had access to the API context, it was easy for the task to avoid conflicts. So losing all of these features, we needed to implement some of them. And now the API, when it needs to run a task, calls the task manager, which is responsible to dispatch the task on Fargate without conflicts. And also, the entry point for the task is the task manager. It recognizes to be run inside the task container, and so prepares the environment for the task and then run it. So what about the API? We expected a maximum of 50 users with very sparse interaction. And the cost of an always-on EC2 instance were really not justified. So with a load like this, usually on AWS, you should opt for an API gateway plus Lambda functions to manage the calls. But FastAPI, it's not really meant to be deployed serverless. But on the other hand, we wouldn't want to rebuild the API again and split them into Lambda functions. So we really wanted to deploy them serverless. We found out that this was really easier than we thought. But first, what do we need? First of all, we need to reflect each API endpoint onto the API gateway, and we want it to be automatic without doing it manually. So we want to redirect all of the API gateway calls into the Lambda functions. And then we want inside the Lambda function to be able to call the right FastAPI endpoint. And we want all of this without having to refactor the FastAPI code. So, as I said, it was easier than we thought, since someone already did the hard work. We used the Mangum library, which does exactly this for you. Given a FastAPI app, Mangum automatically builds a Lambda handler for the app. The handler is able to translate any Lambda invocation into an API call on your app. And all of these while not breaking the main and most important functionalities of a FastAPI. Obviously, there are some drawbacks. The main one is that it cannot handle background tasks asynchronously, since by definition, a Lambda is a function which starts and returns a value, and it cannot continue running in background. But as we said, we already managed this problem by using Fargate. So the resulting architecture looks like this. The user accesses the API gateway. Then this access can be limited. But since we already developed authentication inside FastAPI and Mangum didn't break it, we use that part for authentication. Furthermore, on the API gateway, we didn't really have to map each API endpoint. We just use a generic endpoint and redirect all of the requests on that endpoint to a single Lambda function. The API gateway also automatically manages the load for you. So it instantiates Lambdas as needed. And it also translates the API request into a Lambda invocation for you. Inside the Lambda, as I said, Mangum translates back the Lambda invocation into an API call. It calls the FastAPI app for you, and from now on, it just works as a web server, as you would expect with a FastAPI. When needed, the API can instantiate task on Fargate by calling the EC2 service. And both the task and the API can access the same database and the same permanent storage. So they still share the code base, they just run differently.
There is also a fourth step. Since the EPUB production is part of a bigger pipeline, we needed to guarantee a reliable system. And we chose Daxter to test the correct behavior of the API. I don't know if you know what Daxter is. Actually, Daxter is a data orchestrator, and we use it internally for all our data pipelines. We love it for this reason, and also because we needed to run custom API calls, interact with database quickly, and send daily alerts and logs through Slack. We thought we could treat the reliability pipeline as a data pipeline. Talking about Daxter would require an entire dedicated talk. Here we just show you the reliability pipeline. In green, you can see the steps of the pipeline. Each step is actually a Python decorated function of the framework Daxter. And the pipeline runs daily and check the correct behavior of the APIs, and also verifies that the database is consistent. Now that you have seen all the entire solution, we can share with you also a few thoughts in hindsight. Let's start with the smart choices. We thought we have using Terraform was a smart choice, even though we didn't talk about it, since we changed the architecture many times. Also, going serverless was a smart choice because of the load of the application. And having a shared code base also was a smart choice because it made it easier to handle a serverless application. Having also designed the database from the beginning helped us during the development of the application. Of course, we do also have less fortunate choices. One of them was probably not integrating from the beginning a migration tool, as also Nico said at the beginning. And also EPUB was a problem. Not to blame the library, but using an external library for a critical functionality of the application was not a smart choice in hindsight.
Yes, exactly. But our journey is not yet over. So far we have discussed about alt text, but there are some cases in which alt text is not enough. So let's look, for instance, at this image. If we want to describe this image to a person with visual impairments, it is enough to say that this is the physics formula for instantaneous power, which is computed using force times velocity and their respective unit of measurement. So it can be described in a few lines of text. But if we look to this other example, there is a line graph. And let's imagine we are using this image inside an exercise. We need a way more richer description. For instance, highlighting all the points where the graph intersects. And to do this, we need the so-called long description. And since it is richer, of course, the probability to do hallucination for a large multimodal model is way more. It can happen way more times. So. Up to now, we have seen this problem, but we can have many inaccuracies. For instance, we can have inaccuracies in text, symbols, coordinates in graphs, as we have just seen. Or we can omit relevant details. Or, for instance, for authorial images or portraits, an authorial description is way better than just a generic description of the image itself. While in some other cases, alt text it's useless. Let's imagine we have, for instance, the image of a bus on the cover book of an English book. It's pointless to describe it as the image of a bus, because it's just the cover. Or, for instance, some other images are not accessible by design. Let's think to an English exercise where the student must describe what he's seeing in an image. If we describe it by the alt text, the exercise becomes pointless. So, up to now, we have a quite straightforward pipeline from the artificial intelligence point of view, where we choose between two prompts basing on the subject of the book. But we are going for a more advanced solution. So we want to first classify the image, and up to now we are choosing among standard convolutional like YOLO efficient net, but also large multimodal models. And we are currently evaluating the cost efficiency of each solution. And then, basing on the classification outcome, we can choose a specific prompt, or for artwork, we want to do a DB image search to find the most appropriate authorial description, or if we found a decorative image or images which are not accessible by design, we will just discard them.
We are almost done, so no problem. The presentation is almost over. I just wanted to thank the people who made it possible, who are the real infrastructure, and most of them are here, Milena, Nico, Francesco, Manuel, but also Roberta, Mirko, Cesare, and Antonio, who are here in the audience, but and some of them are at home. And we just want to thank you for your attention.
Okay, thank you so much. Oh, I guess so. Okay, we have got one question. So, which accuracy function do you use for evaluating the deep learning framework? Do you have a human-made testing inputs?
If you want to, go ahead. So we did not develop any particular accuracy function because we are using OpenAI services, so they are developing their accuracy function based on their classification. For our testing, we give our results to expert editors, then review the results on a batch that we control, and based on that feedback, we make some tweaks on the architecture, or on the solution, the whole solution, not the architecture. And maybe I got the question wrong. I don't know if the question was from the audience or from home. So who posed the question? Did I respond to you or any additional comments on that? The audience is a ghost. So, okay.
So we have one more question. So, for the generation of all text, do you add part of the text from the related paragraph in the prompt to provide more context?
Yes, actually, we use the context. Which one? Okay. Excuse me. Okay, this one works. Okay, perfect. So we take the context around the image. At the moment, we are taking the paragraph before the image, and the one after that usually is the caption of the image. If you have suggestions or ideas or comments, you can share it with us, for sure.
Okay, so next question is, how tied is the architecture to the EPUB format? How easy it is to replace it with another ebook format?
Yeah, what we have seen, it's a really small overview of all the processes, but we have a dedicated library which we developed in order to ingest the EPUB, and that's the only point in which you need ebook lib and also beautiful soup. So if we needed another format, for example, we are working on PDF for other projects, and also we are working on other multimedia contents, from which we are extracting the contents. We can implement only that part and then integrate it into the pipeline.
Okay, thank you so much. So we have one more question. Have you used a VLM or fine-tuned VLM for all text?
We still did not fine-tune any LLM on fast text, on alt text, but it is one possibility for the future if we see that the industry solutions are lacking in that regard. But for our application right now, the only issue we have is with the long description. The alt text, the small alt text is already quite good. So we want to focus on that specific part, maybe fine-tuning an LLM or visual LLM to do that captioning for us.
And if I can add a point, of course, this is a crucial step to have a high quality dataset. So this is the first round, and we are doing it using large multimodal model, which are not open source. But in this case, we are doing them. We are correcting the outcomes, so we can have high quality data, and maybe in the future we can fine tune our large multimodal model or just visual language model.
So we'll take the last question. So is a functionality already released with impaired people, or it's still in development?
For us, it's released, but the production will get to the end users in September.
Okay. So thank you so much for joining us here. A round of applause.
Thank you.